SwayamPrabha. Digital India. Educated India.
So, welcome to the NPTEL lecture on architectural acoustics, the fifth lecture today. The fifth lecture is all about the near and far field propagation and loudness. And this fifth lecture is the last lecture of our first week course, and we will go to some other topic in the second week, and the architectural physics, the building physics is going to be end with this lecture. So, if you remember in the last lecture, what we discussed is the sound pressure level, sound intensity level, and how they can be added, and what is the way the particular conversion from the level to the intensity, or from the intensity to the level is going to going to happen. So, in this lecture, lecture number 5, again I have two learning objective. The first one is you have to differentiate the near and far field propagation of the sound by this lecture. Can you differentiate? After the this lecture, if you are going through properly, you must differentiate between that, and then you must correlate between the frequency, sound level, and the loudness of the sound, and that will be the major focus to this particular lecture. So, let us go to the sound intensity once more in a different way. What is intensity? Intensity is nothing but the power per unit area. So, I can write like the power by area is equal to the intensity, and if the power is now further converted to the energy per time, because the energy per time is your joule per second, which is your watt, which is your power, and power per area, that is watt per meter square, is your intensity. Now, this area can be rewrite as the length by volume. Now, further if I see this total things can be rewrite like this volume can be taken into the below this. So, the energy by volume into length by time, and length by time is nothing but the velocity of the wave. So, let us now see how this conversion of the energy and volume can be done. As we know that the energy is nothing but the kinetic energy of the particles which is under the motion. So, it is half into mass into V max square, because the velocity of the particle also will fluctuate, and it is minima and there is a maxima. So, the maximum velocity of the particle is a into omega, and the square of that, and the volume of mass into density. So, if these two are added together in this particular form, then the intensity can be rewrite as half into m a omega square into rho by m, because it is volume now, and into c, c is the wave velocity. So, the intensity can be written in this form. So, you see this is very interesting formula, and you see the intensity of sound is depend upon the velocity, is depend upon the rho density of the media, it is depend upon the amplitude of the motion, amplitude of the propagation, and also it is depend upon the frequency or the angular the velocity omega, and these two are in square terms. So, if I know the frequency, if I know the amplitude and velocity of the sound and the density of the media, I can actually find out what is the sound intensity. Now, go further ahead. So, this intensity is again rewrite as the same equation can be rewrite as this rho c a omega square by rho c, because I have taken another rho c in the here, and then I am dividing that by the numerator, and here I can get two such product and two such parameter separately, and I can write is half into rho p square, p naught square, and z. What is this two? The P naught or the P naught is the pressure amplitude of the wave propagation, which is nothing but your rho c A and omega, and this Z is called acoustical impedance, which is the product of the medium density rho and the wave velocity. Now, why it is wave this pressure? So, let us find out from the units of them. Rho is kg per meter cube and the c is meter per second, velocity, amplitude is meter and this is radian per second is the omega. So, if you just finally come into that, I mean if you just finally rewrite those things and rearrange the units, finally you can come down to the MPa, the megapascal. The megapascal is nothing but your pressure. So, you can see from this particular equation that the I, the intensity is proportional to square of the pressure, and that is why, if you remember in the last lecture, lecture number 4, we have discussed that the pressure square or the intensity is proportional to pressure square, and that is why if you convert the pressure level to the decibel level, you have to multiply that by virtue of 20, not 10. And if you convert the intensity to the intensity level, you have to multiply that by 10, and if because it is logarithmic. So, next slide, in this slide we will see the how the propagation of the sound is occur. The propagation of sound is spherical. It is from a point source and it is going in a spherical way. So, in a air or in a space, it is going in a spherical way. So, from this particular point S source is going in 3 dimensional spherical way. So, the intensity is the watt output divided by the surface area of the sphere, and as in when you move further from the source to the some further distance, your radius of the distance is assumed as a radius, your total sphere that is going to increase, your surface area of the sphere is going to increase, and your total intensity is going to decrease. So, if you are very near to the source, the intensity is very high, because the sphere, the area of sphere is very small. If you go higher distance, larger distance, furthermore from the source or so, your sphere is bigger, your radius is bigger, your surface area of the sphere is bigger, your intensity is going down, and you hear less amount of sound in the level point of view. So, the intensity can be written as W. W is the output watt by 4 pi r square. As you know, the 4 pi r square is the surface area of a sphere. Let us see a small problem. Suppose this is a source of sound S, and it is giving a sound output as 0.005, very small wattage, and you are standing the receiver is standing over here, which is 7 meter away. And if it is so, I will find out what is the surface area of a sphere which is having 7 meter of radius. So, that is why I am finding out the intensity as this W by 4 pi r square, and this is like this, and finally, it is 8.12 into 10 to the power minus 7 watt per meter square. And as and when you got this intensity, which you are actually experiencing here at a distance 7 meter, by virtue of a sound output of 0.005 here, it is easy to convert this to the sound level in that very old formula, the 10 log I by I reference is now you are here and you are listening 59 dB sound. Let us see this particular problem or another problem in a different way. Suppose this is a sound source and you are with a dB meter at point A, you are a receiver at A of that sound, and you are receiving 80 dB at A. The sound pressure level at A is 80 dB, or the sound intensity level is 80 dB at a distance 3 meter. Now, my question is, what will this particular person get, who is standing in B? What will be the SPL or the SIL at B? Thus B is 12 meter from the sound source. I am going to assume it is a spherical propagation, it is a point source. So, first find out what is the SPL is 80 dB. So, first try to find out what will be the intensity at this particular level by virtue of this formula. So, by this it is 10 to the power minus 4 is the intensity at here. If this is 10 to the power minus 4 watt per meter square, which is on this particular sphere of radius of 3, then what is the wattage of the sound output at the source, which I can find out from this equation, because W by 4 pi 3 square is equal to this 10 to the minus 4, and solving this I can get the watt output or the power output of this particular source is 0.0113 watt. And if this is the wattage or the output wattage at the source, what could be the intensity at the B, which is at a distance of 12 meter big sphere. So, that I can find out this W is now this, and this 4 pi 12 square, and this is the intensity level. You can compare the intensity is now very low with compared to the intensity as A. So, I am expecting something less than 80 dB over here definitely, and as I got this intensity B I B, it is very easy to find out this particular level as this old formula by log this by I reference, that is 68 dB. So, this particular problem gives you how from intensity level to the taking consideration of the spherical wavefront propagation, how to find out the watt output, and from watt output to again a intensity in some different distance, and from that you convert that intensity to a intensity level or the SPL. So, the sound output from a suppose a source is W is S, and it at a distance R 1, which is nearer, is the intensity is this, and the SPL is suppose this I 1 by I reference. Now, you go further a further distance R 2, which is higher than R 1, and definitely you will be experiencing less amount of intensity, because the sphere is larger, area is larger, and your SPL 2 is your this. And then let us see, this is going to be happen, because you are if you are near to the source, the intensity is high, your decibel is high, SPL 1 will be higher than the SPL 2. So, what is the difference between them, I am going to find out. So, the difference is SPL 1 is this, SPL 2 is this, and if you just operate this mathematical operation is 10 log A by B. So, I 1 by I reference by I 2 by I reference. So, we can get it like this, I reference get cancelled. So, finally, I got 10 log I 1 by I 2, and now you replace the I 1 and I 2 from here, and you got SPL 1 minus SPL 2. The difference between this two is R 2 by R 1 square, this 2 goes here. So, 20 log R 2 by R 1, and suppose if R 2 equal to twice of R 1, if the distance is doubled, R 2 and this ratio is 2, log 2 is 3, I am sorry, log 2 is 0.3 into 26 dB. So, in case of a spherical propagation, if the distance is double, your decibel level is going to drop by 6 dB. This is the final outcome of this particular the slide. Now, spherical propagation and cylindrical propagation. Suppose this is a unit source and it will give me a spherical propagation, and the examples of the spherical propagations are the some loudspeaker, some human voice, some noise from a small car or something like that. But if suppose there are so many points, multiple point source in a very congested line or maybe very closely distanced linear format. So, then you can superimpose those the sphericals, and it will you will get the cylindrical propagation. So, the what are the examples of that? Maybe a noise from a moving rail, maybe a traffic noise where there are a lot of cars moving one after another, which is the point source, but very closely separated point sources in a road, or maybe an array of loudspeaker in any theater or any maybe any public address gathering field. So, those are the the cylindrical propagation, example of the cylindrical propagation. So, we can actually say it is not a point, it is a cylinder. So, in case of a cylindrical propagation, we will see the propagation is from a cylinder, not from a point source. So, that means it is a line source. So, the length of the line or the length of the source is L, and by virtue of it having a radius, because if you go further away from that line L, your radius is increasing, your surface area of the cylinder is increasing. So, there I will take the same principle, I will what output, that is the power output, I have to divide that by the surface area of the cylinder, and surface area of the cylinder for virtue of this particular geometrical condition is 2 pi r, that is the perimeter into the L. And now, this will be the intensity. So, suppose a length of the source is 100 meter, output is 0.005 watt, what will be the SPL at 7 meter from the line source. So, this we just convert with that, I got this particular intensity level, and again I will take the particular equation, intensity or the intensity reference, I will get 60.5 dB as the decibel level. Now, from the line source, if I go R1 distance, from R1 distance, so I will get the intensity as the cylinder of the radius R1 of length L. If I go to R2, I get this value of I2, and let us find out the what is the difference between the L, the level at R at a distance R1 and R2, and I know this R1 will be higher, the level sound level at this is higher because it is nearer to the source. So, again I will take the operation of that, and very similarly I can find out the what will be the values of I1 and I2 from here, and what is the difference between the SPL1 and SPL2, and this gives me a formula like SPL1 and SPL2 is 10 log R2 by R1, and if the distance is doubled, suppose R2 is twice of R1, then this is 10 log 2, which is 3 dB. So, if it is a cylindrical propagation, if the distance is doubled, the dB level drop by 3 dB. But if you remember in the spherical propagation, it was 6 dB. So, next let us go to the near and far field propagation. Suppose it is the busy road sections, and that is gives me a cylindrical propagation, but by virtue of this propagation, if you now go further in this away from this line, away from the road, this wave front is again going to get a spherical. Suppose if you are very standing very far distance from the road, see road noise will be act as a point source once again. So, some point source gives you a line source, and if you are very near to that particular line source, this is a cylindrical propagation, and now if you go further, that particular line will act as a point, and then it is transformed to the spherical propagation. So, there is a near field zone, and there is a transition zone, and there are the far field zone. So, what happened in the far field zone? In the far field zone, sound is spherical propagation, the sound propagation is spherical. What happened in the near field zone? The propagation is cylindrical. So, if in this near field zone I want to calculate something, I have to assume that this source is a linear source, propagation is cylindrical. Suppose I am here, if I want to find out the same effect of this particular road noise, then I have to assume this as a point source, and I have to assume this is as a spherical propagation. So, if the spherical and the cylindrical propagation or the near field and the far field has to be taken into account. So, in the near field zone, it is dropped by 3 dB by the double of the distance, and in the far field, which is spherical, is 6 dB as per the distance is double. So, by virtue of this, there are two type of sources in case of any kind of the analysis or any kind of the measurement. If you take for any kind of sound the environmental sound, then you have to know that you are in a far field or you are in a near field, and you have to take the specific formula and you have to take the specific condition and then analyze. Now, next go to the loudness. Loudness is a combination of the frequency and the SPL. Now, what happened if in the x axis I have marked all the octave band frequencies, it is starting from the 31.5 to the 16,000, and the SPL is actually written in the y axis, that is in the dB. Now, the human being perceives sound differently. Suppose I plot some points. The first point, let us see, this is the 1000 hertz and 60 dB. It gives me some kind of sensation, and this sensation is very similar when the frequency of the sound is 125 dB and more or less 65 dB and 125 hertz, sorry, 125 hertz sound with 65 dB. For 63 hertz, the same sensation what I am experiencing here, I am getting the same sensation for 63 hertz at around 80 dB. So, if I just plot all those points, which gives me a similar type of sensation with respect to 1000 hertz and some amount of dB, and I can actually create a contour line or a kind of a line, and this is a kind of a loudness. It is a similar loudness or the same loudness. So, loudness of the sound is vary from with these two fundamental parameter of frequency and the SPL. So, this is the loudness, and corresponding to this 1060, the loudness is, this particular loudness graph is called 60 phone. So, by definition 1 phone is equal to 1 dB at 1000 hertz. Similarly, I can plot lot of such plots of in the frequency and the SPL level. So, it starts from 10, which is threshold of audibility, and it goes up to 100, maybe 120 also, which is the threshold of pain, and those blue numbers are your phones, and these red lines are of your the equal loudness path or the equal loudness contour. So, you see in this I can say that this particular band, which is 2000 to 8000 hertz, is very sensitive. This frequency is very sensitive to our ear, because you see this loudness contour curve dipping in over here. So, even a smallest amount of loudness can hear in this particular frequency zone. So, suppose if you want to hear a 30 dB sound of this 4000, you require this much of the sound level 22, but same with 63 you required almost about 60 dB. You cannot hear so 30 loudness sound. This is the equal loudness contour also. Now, how this loudness can be measured? So, suppose I say that I have a sound from a source which gives me 40 phone. So, this is the curve, and another source gives me 60 phones. This is the curve. So, can I say if I do both the sound source, if it is on, switch on, the final sound which is combination of 60 and 40 the phone is equal to 100? No, it cannot be. It cannot be added like that, but because this phone is not a physical parameter, it is a kind of a psychological parameter what a human being is perceived. Suppose this particular graph which we have shown you, this is the equal loudness contour, is for a young gentleman. Suppose if you do the same experiment with the old person of around age of 75 or so, this graph will be shrink a bit. He or she will perceive a different way, different type of some graph, some contour line may be omitted. He or she may not hear that particular phone. So, it is fully psychologically or how the brain is going to map my the sound that way it is devised or it is actually analyzed and derived, and that is why this the unit of loudness, this phone, cannot be added and it is not be justified to add like that. So, we need to add, because there are two different loudness, and why, and this two different loudness has to be added to give a resultant count of a sound loudness. So, we have to take another scale, and that scale should be little bit of a linear scale, and that scale is called Sohn scale. And in loudness, 10 phone increase gives a increment of the twice of multiplication factor of the Sohn. So, if I see this is the loudness plot, that is the from 10 to 100 phone, the corresponding, and this cannot be added, this phone cannot be added. So, this corresponding phone can be translated to a linear format of Sohn, which is showing here in a blue numbers. So, the 40 phone is converted to 1 Sohn, and correspondingly if you go to the next higher phone of 10 phone higher 50, it is multiplied by 2. If you go to another 10 higher 60, this 2 is multiplied by 2 4, and then 8 16 like that. So, the 100 phone is equivalent to 64 Sohn. And now, if you go beyond below 40 by 10 phone decrement, you have to divide this 1 by 2.5, another 10 decrease 20 from 30, 0.5 divided by 2.25 like that. So, it can be now mathematically expressed like Sohn is 2 to the power phone minus 40 by 10. Just put suppose 60. If you put 60 over here, 60 minus 40 is 20, 20 by 10 is 2, 2 to the power 2 is 4, something like that you can with this particular formula we can find out. And in the reciprocal way, a phone can be find out by just virtue of this particular equation. So, you just if you want to find out what is 16 Sohn equivalent phone, put 16 here, log 16 multiplied by 33.22 and add 40 into it. So, now we can actually go into this particular measurement. Now, 40 gives me 1, because I put 40 over here. So, this is 1. Very similarly, I convert this 60 phone to its corresponding Sohn level, which is 4. Now, I cannot add phone, 60 plus 40 cannot be 100, but I can add this Sohn. So, 4 plus 1 is 5, total Sohn because of this 2 is 5. And as I got this 5 Sohn is the resultant Sohn, I can convert that Sohn to the phone by that equation. I put this Sohn as 5, log of 5 into 33.22, and I add with that with 40, it is 63. So, I can say it is not 100 phone. If you add 40 and 60, it is 63. So, that ends this particular chapter, this particular lecture number 5, which is about the near and far field propagation and also about the loudness. And this 5th lecture also conclude the first week of our architectural acoustics course, online course, and this total 5 lectures comprises of some historical development of the sound from the different era, which Dr. Shumana Gupta has discussed in the very first day and our very first lecture, and then the 4 consecutive lecture on the pure acoustical physics or the building physics. So, at the end of this lecture, let us have once again some homework and take away to your home. Let us try this. Try this particular formula, this particular problem, because this will give you a kind of understanding between the near field and far field. Suppose the sound intensity level SIL and is 10 meter from the sound source, SIL at a distance 10 meter from the sound source. you have to find out what will be the SIL at the 10 meter from the sound source. If the SIL at 3 meter from the sound source is 75 dB, first of all you assume it is a near field propagation, where the sound propagate in a cylindrical form, and in second case you assume that as a far field propagation. So, that is a spherical way. So, in this particular videos or in this particular PPTs, sometimes you may see it is a SIL I have written, sometimes it is SPL. Its sound pressure level or sound intensity level, both are actually going to give you in dB scale, and these are related. So, do not be confused with that. Its name suggests its sound intensity level and sometimes it is sound pressure level, but finally, by computation end result is dB is the same. Take a second problem also for your homework, that is, can you find out the loudness of two different sound parameter. Sound source A gives you a frequency of 250 hertz and SPL of 60 dB. Definitely these two combinations gives you some kind of a phone, and sound level sound source B gives you of a frequency of 4 kilohertz and SPL of 70 dB. That also converted to a particular the phone in loudness contour, and then you add these two together, both the sound source A and sound source B, the effective or the resultant the loudness you have to find out. So, those are the references, and that is the end of the lecture number 5. Hope you understand the lecture well, and if you not, go through the lecture once more, and you can also contact us, and thank you very much.